In this video, we will be taking a look at the definite integral, which is really the main concept in integral calculus, just as the derivative was the main concept in differential calculus. Now, from your previous studies, you've learned that the area under a curve can be approximated by rendering that area into rectangles and simply adding up the areas of the rectangles. Now, if you take a look at this expression right here, just looking at it, just breaking it down, what we really have here is this would be the height of each rectangle. So simply evaluating at different points along the x-axis the y value, the corresponding y value, to give us the height of the rectangle, whether that be the height on the left side of the rectangle, right side of the rectangle, or midpoint. We've looked at sort of all three methods. And then multiply that by the width of each rectangle, right? So height times width, or length times width. Those two right there give you the area. Now, the sigma here represents the sum of all of those areas, and the n represents the number of rectangles, right? So, of course, you have a better approximation with 8 rectangles compared to 4, and you have a better approximation with 16 compared to 8. But if we allow n to tend towards infinity, where even if we have 1,000 rectangles or 1,000,000 rectangles, we get a better and better approximation. So if we let the n, or the number of rectangles, tend to infinity, then at its limit, we will actually get the exact area underneath the curve. So that's where that definition comes from. And again, delta x would be the width of each rectangle, and xi would not be the length, because f at xi, f at each of those xi's is would be giving us the height, but xi would be the point at which we're taking the height. Okay, so point at which, at which height is determined. Okay, and so we need to know one other thing here, and this is the official definition of the definite integral. So if f is a continuous function defined on an interval, then the definite integral of f from a to b is given by this notation. So again, this is the notation that we use for integrals in general. So you've got this little S-like shape that kind of goes like this, and then the limits of the integral would be placed there, with the lower limit down here where a is, the upper limit where b is. F, which of course is the upper boundary function, or the curve. And then this notation here sort of tells us that it's in terms of x, right? So I sometimes look at this as, this is analogous to the delta x over here, just as this f is analogous to this f over here. But the other way to look at this is, instead of looking at it as multiplication, the dx actually just goes with this notation. It's as if this notation here is the open parenthesis and this notation here is the closed parenthesis. You need both. You can't just have you just can't have one without the other. Okay, so this would be interpreted as the integral of f at x from a to b in terms of x. Okay, and I think the meaning will sink in a little bit more as we begin to use the notation. Okay, but all of this is simply equal to what we had talked about before, which is really the areas of the rectangles as the number of rectangles tends towards infinity, because you see that is a definition right here. Okay, so when the function is greater than or equal to 0, the definite integral simply represents an area, as we've seen before, right? Because it's defined this way, as the area. In general, however, if a function f takes on both positive and negative values, as many functions tend to do, then we interpret the definite integral as the area above the x-axis minus the area below the x-axis. Okay? So that's really key. So if you have a function that looks like this, right? So from, say, 0, let's use a different color here, from 0 to, I don't know, maybe this is 2, then if we were to figure out the definite integral from a to b, then that would be the area above the x-axis. Okay, so maybe those two areas combine to give you, I don't know, 3 square units, minus the area underneath the x-axis. Okay, so maybe that area is like 2.5. So then in that case, the definite integral is going to be equal to 0.5. Okay. All right, and one other thing that we're going to do in a subsequent video is we're going to take a look at how to determine the definite integral from scratch, or really from first principles, or really from this limit definition. And in order to be able to do that, we will need to know sort of these 3 sums, right? The sum of the natural numbers starting with 1 up to whatever natural number is given by this expression. The sum of the first n squares is given by this expression, and the sum of the first n cubes is given by this expression. But more on that in a subsequent video.